the changing groups here. You also had a methoxy group, you had another methyl group there, and also, so it was just change of the subsequent of the pyridyl ring that gave us the first drug, and our first drug was what we are calling omeprazole. So more potent, but they did enlarge the thyroid gland, and they also cause inflammation and crosses in blood vessels. So those are the benzimidazole, the benzimidazole, the timoprazole. The shortcomings were that they did have a lot of toxicity. So again, small structural modification was done until a safe drug, which is omeprazole, was discovered. So that's what we have just said, that after timoprazole, then more, there was change, or there was a further structural modification, substitution. We have seen why we are substituting. So there was further substitution on the pyridyl ring. You can see there is a methoxy group, 2 methyl groups, and there is a methoxy group para to, this is para to the pi nitrogen of the imidazole ring, para to the pi nitrogen of the imidazole ring. There is a methoxy group, and we have said those substitutions, both on the pyridyl ring and on the benzimidazole ring, were important to reduce toxicity. Now, as I said, omeprazole and esomeprazole are the same structure. The only difference is, of course, because of this sulfur. Remember, just as we said of the carbonyl group, whenever you have these groups, like these rigid groups, when you have some of these rigid groups, then you can allow for this one, you're allowing for stereochemistry, for optical isomers, optical isomerism, where you can either have the E or the Z isomer. Remember, the E or the Z isomer, and the E, which is the esomeprazole, was found to have much more activity. We are going to discuss why it has more activity. The more activity is mainly because of the differences in metabolism. The increased activity of esomeprazole, it's not because of its better binding to the receptor, but more or less is because of the differences in the metabolism between the omeprazole and the esomeprazole that results in the change of activity. So that is important for us to note. If you go out there, you will get omeprazole. Omeprazole is a racemic mixture which has the E and Z isomer, or the R and S isomer, whereas the esomeprazole, the esomeprazole, not the R, but the E, sorry, the E and Z isomer. The R and S are the geometric, so the E and Z isomer, whereas esomeprazole is the pure isomer, the pure optical isomer, just as we talked about when we were talking about the third generation, when we're talking about the third generation anti-allergy or H1 blockers, third generation H1 blockers, we did mention you can do resolution, you can purify to get the pure isomer, and sometimes the pure isomer has better activity. So the same case applies to omeprazole. Look at it, similar structure, but difference in stereochemistry has a very big influence on the metabolism, giving one drug advantage over the other in terms of potency, giving one drug advantage over the other in terms of potency. It has now done the same thing. I don't know why it keeps doing that. We move on. I don't know why it decides to do that. So we have discussed that slide, or we are saying optical or stereochemistry can influence the metabolism of drugs, and that indeed happens for quite a number of drugs. So stereochemistry can influence the binding to the receptor, where one isomer has the optimal size to bind the receptor optimally, or it can influence the metabolism, where one drug perhaps is being metabolized more slowly than the other one, and therefore having one drug having higher activity than the other. I don't want us first to look at that. So let us look at some of the examples of these drugs. We will look at the activation in a while. So some of the examples of these drugs, we have omeprazole. We have already looked at the structure. We have said it has a methoxy group in that ring. It has a methyl group there. It has a methyl group here. It has a methoxy group there. So if you look at lansoprazole, it does not have any substitution on the benzimidazole. It has two substitutions, including, you can see that it's a trifluoromethane methoxy group there. So you can see it has that group there, and it has a methyl group there. Again, if you look at rabeprazole, again, no substitution on the benzimidazole, but quite a big substitution on the pyridyl ring, and also a methyl group there. If you look at pantoprazole, of a lot of interest, pantoprazole, it has two methoxy substitutions on the pyridyl group. Please look at this group here. It has, if you look at this group, it is a trifluoromethane group, so it's a trifluoromethoxy group. So this group here, if you look at this CF3, this group is an electron withdrawing group, and we will be able to see that it has a slight effect in the activity or in the potency of pantoprazole as we move on. So when we look at these drugs, we can see they are obeying what we have talked about. They all do have the pyridyl ring, they have the benzimidazole ring, they have the sulfoxide group, and all of them have this methyl group at that particular point. They do have substitutions they might not have substitutions on both rings, but at least they have substitution, especially on the pyridyl ring. They do have substitution on the pyridyl ring, and we will note that the pyridyl rings, for these drugs to have activity, these drugs are usually prodrugs. And because they are prodrugs, they do require to be activated in the body. For them to be activated, they require protonation. And the protonation starts with the protonation of this nitrogen there. So this nitrogen requires to be highly, highly basic for it to accept to be protonated. And thus, when you have the substituents in this ring, you require substituents that will push electrons into the ring to increase the basicity of this group, or to increase the basicity of that group. And if they're increasing the basicity, we discussed yesterday, if you increase the basicity, do you increase the pKa or do you decrease the pKa? We discussed it the last time. You are increasing the basicity of this group. When you increase the basicity of this group, do you increase pKa or do you reduce pKa? Can I get answers? You are increasing the basicity of the pyridyl nitrogen. Do you increase pKa or do you decrease pKa? Increasing basicity of the pyridyl nitrogen, do you increase pKa or do you decrease pKa? Can I get an answer quickly? I can see Kadia increase pKa. Somebody else? Do you increase pKa? Do you decrease pKa? Let me get several answers. This is easy. Increase pKa, correct. You will increase pKa because the higher the pKa, the lower the Ka. And the lower the Ka, the higher the basicity. In simple terms, the lower the Ka, the higher the basicity. So what we are saying is that we want to decrease the pKa, we want to increase the pKa, we want to increase the pKa. In increasing the pKa of this nitrogen here, we are increasing its basicity. even if you can't, yeah, you are increasing its basicity. So the higher the pKa of nitrogen, the higher its basicity. Once it has a slightly higher basicity, then it will be easily protonated. Remember, these drugs will move all the way, will be absorbed, and they will be trapped. They will move into the canaliculus where we mentioned, and in the canaliculus there is acidity. The canaliculus has high acid, and therefore these drugs are trapped within the canaliculus. This drug will be protonated, and once it is protonated, so the first one to be protonated is this one to be protonated. The next one requiring to be protonated is this one. So the pyridyl is protonated, and then next the benzimidazole is protonated. Once you have that one protonated and that protonated, then there will be in equilibrium. Whenever you have weak acids and weak bases, there will be in equilibrium, the protonated in equilibrium with the non-protonated. That we know. That anything that is protonated, like these are weak acids and weak bases, these are Lewis acids and Lewis bases. So because it is a Lewis base, then it will be in equilibrium with the non-protonated at any time. So the pyridyl, so you will have protonated there in equilibrium with, let's say, protonated there, non-protonated there, plus non-protonated there, protonated there. I hope you can draw that. Like all I'm saying is, if you look at this drug, it has two areas of protonation. Like you can call this pyridyl. When this pyridyl, you can give it a P. When it is you will have the first molecule P pyridyl pH positive for pyridyl, plus let us call this benzimidazole, we call it BH positive. So you can have pH positive plus BH positive. That is on one side. Then in equilibrium with, at one time you can have pH positive plus this one, the way it is. Again, in equilibrium also with this having positive and that one not having positive. And it was found that the molecule that indeed gives us highest activity is that molecule when you have this protonated and this one not protonated. This protonated and that one not protonated. But the first move, please let us get it correctly. The first move for the activation of these drugs is protonation of that nitrogen and protonation of that nitrogen. Those two moieties, that is the dications. That is what we are calling the dication. So we can even put it as one. We can actually write it as one ion. We say that you have P positive, B positive. P positive, B positive will be in equilibrium with P not protonated plus B protonated, or it can be in equilibrium with, so it will be in equilibrium. We have said it will be in equilibrium with the molecule P B H protonated plus, let us put we are joining them both, so it will be in equilibrium with this. We are calling it the pyridyl, so we are calling it P, the P not protonated in combination with the B protonated BH. So that one will be one form, plus the P now protonated and the B not protonated. So the equilibrium where we have, so we are starting with on one side, that is on the left side, we have B pH positive plus BH positive. So both of them, the two nitrogens are protonated. Then you put your equilibrium sign. And once you put your equilibrium sign, now you can have, in one of the molecules, you can have the P not being protonated, but your N, your benzimidazole, that is the B is BH positive. That is in equilibrium, is together with plus the other molecule will be the B is not protonated, so the B is plain, plus now the pyridyl one is protonated and the pyridyl one is the pH positive. So but I am saying the protonation of both must first happen, and then creation of an equilibrium and the moiety which is found to trigger off or to start off to formation of the active product is when nitrogen is not protonated, or when nitrogen has the highest nucleophilicity and this one is protonated. So this will have a hydrogen, this will not be protonated. And when that happens, that nitrogen, which is not protonated, it is a Lewis base, attacks that carbon there. And that now triggers the first step in the activation of these molecules. And you will see all the structures are the same. So that we're going to look at it in a minute. Particularly, what is important when we look at these structures is to understand that they have structural resemblance, and indeed, because of the structural resemblance, they are acting on the same receptor, and of course also to understand that all these drugs are drugs. None of them is active. They must be activated in vivo for them to have activity. Let us look at their chemistry. The proton pump inhibitor, pharmacophore, is a 2-pyridyl methyl sulfonyl benzimidazole. Let us go back. I think it is either Apambele. Yeah. So this is, we are looking at this, and we are saying this is the pharmacophore. And why are we calling it? All the drugs must have this area. So this is the pharmacophore. What we are changing is the substitution at position 5. That substitution there. But all the drugs must have the pyridyl. That is the 2-pyridyl. So the pyridyl, 2-pyridyl methyl. 2-pyridyl methyl. There is this methyl group there. 2-pyridyl methyl. The sulfonyl. So because of this, so why they are calling it 2-pyridyl methyl. Then there is the sulfonyl, and then there is the benzimidazole. So that's why we are calling it 2-pyridyl methyl sulfonyl benzimidazole. That is the pharmacophore of these drugs, and that must be present. What you are allowed to change are the substituents on the pyridyl ring and the substituents on the benzimidazole ring. And in changing those substituents, you can be able to change pKa1 and pKa2. Remember, we said the higher the pKa, the lower the Ka, or the higher the basicity. So you want to do substitution here so that this pKa1 is quite low to allow for rapid protonation. So we are saying it is a 2-pyridyl methyl sulfonyl benzimidazole proton pump inhibitor pharmacophore with pKa1 and pKa2 sites as identified there. So that is the pharmacophore. I hope we understand what we are talking about. Again, numbering, very important. We start with the pyridyl nitrogen. There. And then that is position number. So that's position 1, position 2, position 3, position 4, position 5, position 6. So when we come to the benzimidazole, please make sure you put the prime. So this will be again on our telenitrogen as we want numbering. We are first, this is the imidazole ring. So we start with our telenitrogen, 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime, 7 prime. So make sure you do that differentiation. We haven't done it there. Now we are I didn't, sorry, I think it was the first year. I think I had moved. Okay, yeah, right. So we are saying the PPI pharmacophore is a 2-pyridyl methyl sulfonyl benzimidazole. All of us now understand that. They differ only in the nature of the substituents placed on the pyridine and benzimidazole ring. We have looked at that. The electron donating or withdrawing nature of these substituents has a significant impact on chemical reactivity and onset of anti-secretory action, because we are saying those 2 nitrogens, the pKa1 and pKa2, will depend on the type of substituents that you have. If you have electron donating substituents, they will enhance the basicity of those nitrogens. If you put electron withdrawing groups, they will reduce the basicity of those nitrogens. And then when that happens, definitely the ability to be protonated will it also implies that the rate at which the conversion, the activation of the prodrug, the rate of activation of the prodrug to the active drug will also be slow. Of course, the potency will also be slow because of the concentrations. Remember, once the rate of protonation is low, then the concentration of the various moieties is also low, and therefore the potency will be low. So that is very important, that the pharmacophore, the 2-pyridyl methyl benzimidazole moiety is the same, and it's the substituents that determine the rate, the potency, and the onset of activity. The sulfonyl moiety found in the parent PPI structures is not sufficiently reactive to form the essential disulfide bond with the proton pump, and therefore it was sulfonyl first, but it was converted to a sulfone. So we are saying the sulfonyl moiety was not good enough. It was oxidized to give us the sulfoxide group, which increased the potency of these molecules. Must first be activated through 2 protonations and a subsequent spontaneous rearrangement to form the active sulfenamide or sulfenic acid derivatives. All we are saying is that these drugs are prodrugs. And for them to bring about any activity, they must receive 2 protons. Those 2 protons, as I have said, one will go to the pyridyl nitrogen, the other one will go to the benzimidazole nitrogen. After the first protonation, then there is formation of equilibrium, and the moiety which has the benzimidazole protonated and the pyridyl not protonated is the one now that continues with the reaction, whereby the pyridyl nitrogen attacks the carbon 2' to continue or to trigger or to further navigate or to further push the reaction to the right. So I hope that is clear. So we are saying it is important for us to understand that the protonation of the 2 nitrogens must first occur. Once it occurs, there is formation of an equilibrium. And the one where the pyridyl is not protonated, because the pyridyl, which is when the pyridyl is not protonated, then that nitrogen has much higher pKa. That nitrogen has high nucleophilicity. It will attack the carbon 2', which is highly electrophilic, and that will trigger the activation reaction. We are going to look at that in a minute. So all I want us first of all is to understand the need for activation means that the PPIs are inactive as administered. Of course, they are. That is true. They are prodrugs. 2 protonation reactions occur readily in the highly acidic parietal cell, as I said earlier. Pyridine nitrogen and the double-bonded benzene nitrogen N3. So the pyridine nitrogen is protonated, and the benzene nitrogen N3 is also protonated. Remember the other one, the thiol nitrogen already has a hydrogen, so that cannot be protonated. The one that can be protonated is the one we are calling the nitrogen 3 in the imidazole ring, that is a pi nitrogen. The pKa of the pyridine nitrogen, that is pKa1, runs from 3.83 in lansoprazole and pantoprazole, 4.06 in omeprazole, and its pure S isomer, esomeprazole, and 4.53 in labeprazole. So you can see it is lowest in lansoprazole and pantoprazole, and the lower the pKa is, the lesser the activity of that molecule in terms of protonation. There could be other factors that can govern its reactivity, but when you look at the pKa, then the lower the pKa, the lower the pKa, the higher, the lower the pKa, the higher the Ka, and therefore the lower its basicity, and hence the lesser its potency, or the lesser its reactivity. These pKa1 values ensure that the pyridine nitrogen of all the PPIs will be almost completely cationic at low pH 1.3 of the parietal cells, thus trapping the drug right at the site of action. So that is one very important role of the protonation. Once you protonate the pyridyl nitrogen, almost all, but not all. So there will still, remember, when you protonate, there will always still be an equilibrium. What will happen is that there will be a very low concentration of the one which is not protonated. But the minute the one which is not protonated is consumed, more Yeah, remember, we have always said you must always have a balanced equilibrium. So once you consume whatever is not protonated, more will form so that the equilibrium is balanced. But all we are saying also, because of that protonation, once you protonate a drug, it is ionized, it is charged. It means it cannot penetrate the membranes. So that drug will be retained, or that drug will be retained, or what we are calling trapped, within the parietal cell. Remember, this drug moves and gets into the parietal cell. It will be retained there through protonation, and that is how it's concentrated within the parietal cell, and that is why it is, in fact, and the advantage is where it is concentrated within the parietal cell, as we studied earlier, that is also where you have your hydrogen potassium ATPase pump. So where this drug is being concentrated is also near the site of action, and that indeed also reduces the toxicity and improves on the selectivity of this drug. So that's the first step: trapping of these drugs through protonation within the parietal cell, within the canaliculi system, trapping them there, because that is an acidic area. Once they are trapped there, then they will be ready. They are in high concentration. The receptor, which is the ATPase enzyme, also is in close vicinity, and therefore they will readily bind the receptor and hence inhibit it to the maximum percentage. They will be highly effective because the receptor is near, the concentration is high enough. They are trapped within the parietal cell, and therefore optimal activity. Equilibrium equation, as I've been trying to tell you. So we are looking at you have the anionize conjugate, you have where the benzimidazole is protonated, and you can have the pyridine group is unprotonated. This is the one we are saying is the one which we require to attack. This is the one we are saying, the one we require to initiate, is the one we require to initiate the activation of the PPI. But initially you get all of them protonated. That is important for them being trapped within the parietal cell. So generates the activated form of the PPIs by conducting an intramolecular. Remember, intramolecular means within the same molecule. Within the same molecule. An intramolecular nucleophilic attack at carbon 2 position of the benzimidazole. Then electron donating substituents on the pyridine ring, especially at the R1 position, will push electrons to the pyridine nitrogen and increase the percentage existing in the cationic form. Let us now, so that when we look at this, you understand what we are talking about. Let me look for I think it's before this, sorry. We go back. I want you to understand what we are talking about. Yes, we can look at it from the two. We can even look at it from here. So all we are saying, the drug has been able to pass through all the lipid membranes, and now it is within the parietal cell. You can see this is our parietal. So this is just to show that the drug has passed from the blood. It is now within the parietal cell. When it gets into the parietal cell, we have said the first thing that happens is double protonation, and that is why we are saying plus 2 hydrogen protons. I'm sorry if it's not very clear, but I'll explain. These are 2 protons. So here we have 2 protons there, and those protons, as we have said, will go for the pyridine nitrogen and also the benzimidazole nitrogen. So you can see that is protonated, that is protonated. This double protonation is what we are saying, we are calling now. We can call this is pyridine, PYRH positive, benz BH positive. So this molecule is the one we are calling pyridyl benzimidazole protonated ion. So that is completely protonated, where the pyridyl nitrogen and the benzimidazole nitrogen are protonated. Then, as I said, this you can put now an equilibrium here. You can add that for yourself. Draw an equilibrium there. Once you draw an equilibrium there, draw that this also will be in equilibrium with when this, you have this, you remove the hydrogen there, so that is not protonated, and that is protonated. Plus, You remove the hydrogen there, so that is not protonated, and that is protonated. So it will be in equilibrium with, so this double protonation will be in equilibrium. So this is a dication, will be in equilibrium with two monocations. One monocation where that is protonated, the other monocation where that is protonated. I hope that is clear enough. So that is what we are saying. And that is being shown here now, where we are saying you're losing one proton. This is -1 proton. And once you lose one proton, then what happens is that once you lose one proton, this becomes highly nucleophilic. And that is the next, that's what you're seeing here. And because this is highly nucleophilic, that nitrogen attacks this carbon. This is carbon 2 prime. This is 1 prime. That is 2 prime. This 2 prime is, this carbon is highly electrophilic. Why? Because if you look, it is joined to a sulfur, which is joined to an oxygen, and that's why we said the sulfide group was found not to have a very good activity. But when they put an oxygen, which is highly electron withdrawing, the whole of this group was withdrawing electrons from this carbon. So this carbon had a delta positive, and because it has a delta positive, highly electrophilic, it facilitates or enhances the attack of the nucleophilic nitrogen on the electrophilic carbon. So that attack happens, as you can see, when you lose one proton. So it happens when that nitrogen is not protonated. When that happens, this pushes there, class, that pushes there. If that pushes there, this carbon will have 5 bonds. So this bond here, double bond, migrates to that hydrogen, and therefore that hydrogen also is no longer protonated. No, it's no longer, it is protonated, but it is not carrying a positive charge, because, as I have said, this attacks there. Once it attacks there, there was a double bond there, those electrons satisfy there, and that now has no charge. So that is our first molecule that is formed, and this is the molecule we call the spiro intermediate. That is our spiro intermediate. You can see these are all equilibriums. The spiro intermediate now is in equilibrium with this other molecule. How does this happen? You find, so you have this nitrogen here, see that this nitrogen here, so this there, minus. Yeah, so you have, this is a spiroketo. The next thing that happens, you have this nitrogen here with the hydrogen. There's nitrogen here, which is protonated, and that bond moves in there. So you get a double bond there. Get a double bond there. When you get a double bond here, this carbon has 5 bonds, so it forces this to cleave. And once that cleaves, then it comes a sulfur going to oxygen, and the oxygen takes up the proton that comes from there. So this becomes an SOH. So that is how the next one is formed. I hope it's clear. So it's only that this nitrogen here, this H moves, that moves there. Here you get a double bond there. It forces this bond to break, moves out, and then this now is a proton there joining there to form an OH, and that is what you call sulfenic acid. So you can see these are just equilibriums. So we have said our spiro intermediate is in equilibrium with our sulfenic acid. So that's our sulfenic acid. Then now the next again is another nucleophilic attack. Now this nitrogen, you can see it has a lone pair of electrons, highly nucleophilic. It initiates an attack there on that sulfur. Nitrogen, lone pair of electrons, attack that sulfur. This hydroxyl, this OH attaches with the hydrogen. Remember, this is in acidic media, so this is coming out as an OH minus, because this lone pair of electrons attack there. These electrons come to this, so this is coming out as a hydroxide ion. It attaches itself to a proton, and therefore you lose a water molecule. So now This was a sulfenic acid. Then it forms our next compound, which is a sulfenamide. So now that loses a water molecule, and now gives us this molecule here. So it's just this nitrogen, this nitrogen here, it has come here. So now this becomes a 6-membered ring. So you can see now the easier way to remember it is that you have 2 6-membered ring. The 5-membered ring is still there, but now 5-membered ring has really not changed. And then, of course, the other ring has not changed. So the benzimidazole is still in existence. You can see our benzimidazole is still in existence, but our first ring, our first group, the whole of this group is the one which undergoes cyclization, and now you can see we have a tetracyclic moiety, which we call the sulfenamide. Now this sulfenamide is highly reactive, and this sulfenamide is now, which this sulfenamide highly reactive, and you get the ATPase enzyme. So these are ATPase enzyme. The ATPase enzyme usually have a sulfhydro group, an SH group, and the ATPase enzyme now comes and attacks there, and that cleaves, and you get your disulfide. So the ATPase enzyme, through its sulfhydro SH group, through its sulfhydro group, comes and attacks there, attaches onto this sulfur, that breaks, and you can see now the difference is that we do not have an equilibrium. The adjunct formed, because it's an addition. The ATPase enzyme has been added onto our activated moiety, which is a sulfenamide. The adjunct formed, you can see it is stable. You can see the difference. All these other ones were equilibrium, but you can see this is one arrow, which is it's one arrow, and it's not an equilibrium monodirectional arrow, and therefore monodirectional arrow means that once this compound is formed, which is the adjunct, it is a stable moiety. This moiety now, you can see what it has done. It has bound the ATPase enzyme. And of course, once you bind the ATPase enzyme, what does that mean? The ATPase enzyme is not available to catalyze the pumping of the protons into the gastric lumen, and therefore you block the release of the protons. And basically, that is what happens. That is the mode of action or the activation. This arrow here is saying also it does not have to go through the sulfenamide. It can also be converted directly from the sulfenic acid. It can bind directly. Sulfenic acid can also bind the ATPase enzyme to give us the disulfide, which indeed is what we are saying is the stable molecule which is holding the ATPase enzyme, and the ATPase enzyme is not available. And once it is not available, then it cannot catalyze the secretion of the acid. Once you do not secrete acid, that means you will not have acid in the lumen, and therefore the drug will have worked. Because remember, we are reducing the amount of acid in the lumen to minimize the irritation the acid causes on the ulcer. So once you reduce the acidity in the lumen, you reduce the irritation that acid causes on the ulcer, and therefore that will cause relief. And once you do that also, you will give time. That means you will allow the ulcer to heal because it is not being irritated. It will now, that's why we give other drugs, like, when we give the PPIs in the management, especially of those ulcers where you have the H. pylori, you give with other antibiotics. So you will give is clarithromycin. In addition, there is amoxicillin, and sometimes you even put metronidazole, but which was found to be very irritating. But once you give it with combination with those other drugs, then it will help in the healing. It will help in the healing of the ulcer. Further, because as the ulcer heals, you do not have any acid to come and erode it, because you can imagine you are healing and then all of a sudden a lot of acid, it's eroded and it will never heal. So that is the method, the mode of action of the PPIs.